Now, in the last class, we had seen what thermodynamics is all about, that given a thermodynamic system, how do I describe the given a thermodynamic system, that we describe the system using a macro set of macroscopic variables. Today, our starting point of the discussion is with the laws of thermodynamics. Now, these laws are essentially, they originate from our common experience, and we know that there are three laws: the zeroth law, the first law, and the second law. Now, the zeroth law is very simple. What it says is the following. Let's say I have three systems. I have three systems. I'll call them as A, B, and C. So I have these systems, which is A, I have this system, which is B, and then I have this system, which is C. The statement of the law is the following. If A and B are in equilibrium, let's do it the other way around so that it is easier to, well, you can do it any way you want to do it. If A and C are in equilibrium, and if B and C are also in equilibrium, then it follows A and B are in a joint equilibrium. So essentially the statement of the law says that if A and C are in equilibrium, B and C are in equilibrium, then it necessarily means that A and B are also in equilibrium. When I say equilibrium, this essentially means that there's a joint equilibrium between these two. Later on we will essentially clarify what we mean by an equilibrium. For a thermodynamic system, you understand that there are so many macroscopic variables. Equilibrium would necessarily mean that there is a mechanical equilibrium, there is a thermal equilibrium, as well as there is a chemical equilibrium. Now, clearly, let's say the system A that I have is characterized by a set of macroscopic variables which are A1, A2 all the way up to, let's say, N. Similarly, system B is also characterized by B1, B2. I can have different N, but let's keep it the same way. And then system C is characterized by C1, C2 all the way Cn. So these are my macroscopic variables which we discussed in the last class, which describes the thermodynamic state of the system. Now, that describe the thermodynamic state of the system. Now, when I say that A and C are in equilibrium, that necessarily means that I can have a relation of this form, a functional form, between the macroscopic variables that describe the thermodynamic state of A and the macroscopic variables of the thermodynamic state B. The function f can be different for both of them, but for ease of this discussion, we will assume them that is true. So therefore, if A and C are in equilibrium, it follows that I can recast my equation in the following way. I can have A1, A2, AN, C1, C2 all the way up to Cn is equal to 0. Similarly, if B and C are in equilibrium, then it follows that I can have B1, B2, Bn and C1, C2 all the way up to Cn to be 0, right? Now, from these above relations, it's obvious I can write down C1 as some function of A1, A2 all the way up to this, but then I will write it down like this way, and similarly from the second equation it will follow that I can make C1 or take the C1 on the right hand side and write it down, and I will have, I'm sorry, this is, so Bn, and then I'm going to have C1, C2 all the way, sorry, no longer C1 because I have already made C1 as my subject. C2, C3, Cn. So I can have these two functional relation. So since the left hand side is the same, therefore it follows f of AC, A1, A2 all the way up to An, C2, Cn is equal to right. So this is one of the equations that I have. Everything is fine with this, but now comes the zeroth law. Zeroth law also says that if A and C are in equilibrium, if B and C are in equilibrium, so we will write it down like this way, if A and C are in equilibrium and if B and C are in equilibrium, that necessarily means A and B are also in equilibrium. So it follows therefore I should have an equation that tells you that f of AB that describes the joint equilibrium of this. Together with this equation, of course, I have f of A1, A2, An, C2, Cn is equal to f of B1, B2, Bn, then C2 all the way up to Cn. So this essentially forms the crux of the zeroth law of thermodynamics. So this looks very simple. There is nothing complicated in this particular thing, right? But now, if I look at the second equation, then I can choose any set of parameters in AB, right? I can choose any set of parameters. If I look at this equation, the top equation, I can choose any set of parameters AB and substitute this in 1, right? So let's call this equation 2. Well, it's the other way around, but this one we had earlier, therefore we'll call this 1. So I can choose any set of parameters in A1 and A2. So if I increase one of the parameters in A, then the corresponding parameter in B should also decrease, so that this constraint equation in 2 is satisfied. So I can choose any of this parameter without changing C, without changing any parameter in C. This resulting equality, so if I change, let's say A1, then maybe there is a change compensation in B1, right? But you see, there is no change in C, right? There is absolutely no change in C. So therefore, it follows that any variation of these parameters that moves along the manifold which is defined by this, any variation in AB which you do as you move along this manifold which is defined by 2, equation 1 must remain valid. Hence, you conclude that the equilibrium, the zeroth law, these two equations together must tell you that something, let me it tells you that there must be an equation. So the constraint, the variable C2, Cn in equation 1 on the both sides must drop out, because we have already seen that if I make any change in A1 and A2 that lies on this manifold which is defined by the equation 2, the equality is still valid without changing anything in C. Therefore, I must have this one essentially means that there is a state function which is a function of the thermodynamic variables that describes the equilibrium state of the system that remains constant, and we call this the empirical temperature. This is the first concept of temperature that enters thermodynamics, and that enters through the zeroth law. What about the first law? The first law is very simple. It's essentially a statement of the conservation of energy. And the statement is the following. Suppose that I have a thermodynamic process in which no heat exchange is allowed. As we go on further and further, you will realize that no heat essentially means an adiabatic process. We will slowly give you the terminology as we go ahead. So in which no heat exchange is allowed, then the work done depends only on the initial and the final points, or in a different way, the work done does not depend on the work done does not depend on the path taken, but rather depends on the initial and the final points. Now you want to ask, what do you mean by a path taken? Right? The path taken is in the space of your macroscopic variables, which we shall call x, or let's not put a vector sign right now. The path taken in this space. For example, for a hydrostatic system, the PV diagram. In the PV diagram, if I take the system from one point to another, let's say like this way, and if it's an adiabatic process, which means there is no heat that is allowed to be exchanged with the environment, then it follows the work done, delta W, does not depend on the path that you have taken, but it only depends on the initial and the final point. Now this is very, very similar to what we do in mechanics. In mechanics, we say that whenever I have a conservative force field, I know that the work done depends only on the initial and the final points. And from this analogy, from this definition, you essentially bring in the concept of the potential energy. In thermodynamics, So this adiabatic process is synonymous to a conservative force field in mechanics. So here also I can see that the work done does not depend on the path. Therefore, clearly, if I just draw the analogy between mechanics, then I can write down this work done as a difference between this. So delta W is U of xf minus U of xi, where U is now we called it as an internal energy. So the work done depends only on the internal energy of the system, on the change in the internal energy of the system. If I remove the constraint of adiabatic process, which means that the system is allowed to exchange in heat during going from the state A to B, then the general rule is delta Q is delta U minus delta W. Now remember, delta is always infinitesimal change. If I want to change it, I can write down this in this particular form, but I have to be careful that I put a cut on the two derivatives over Qn. So this is d cut Q and this is d cut W. The reason I have written it like this way, because here d cut Q and d cut W will depend on the path that is taken. So if it's not an adiabatic process, if there is a exchange of heat that is allowed, which means if I go back to my PV diagram, so if I go from here to here, I can either go like this way or I can go like this way, right? And if it's not an adiabatic process, this is a pressure volume diagram. The system either goes from A to B via this straight line or it goes from this. The work done would be different in the two cases. So therefore, the cut essentially tells you that these are path dependent quantities, and the quantities which are path dependent are essentially what is called inexact differentials. Quantities which are not path dependent, such as the internal energy, are called exact differentials, which essentially means that if u was a function of x1, x2 all the way up to xn, then I can write down the infinitesimal change du as sum over I del u del I del xi dxi. This is for an exact differential. So we shall do it very briefly. How do you differentiate between an inexact differential and an exact differential? An inexact, so let's just do it over here. An inexact differential, for example, if I have a function df, which is, I can write down this as dx plus b of xy dy, right? This is the change in this function. Now remember, when you, for a single, if you have done calculus of a single variable, then I know that df is df dx times dx, right? But now this is calculus of many variables, so there are more than one variable. More, so if there is a function which is dependent on x1, x2, x3, xn, I have a function which depends on x1, x2, x3, xn, then the change in the function, the total change in the function is del f del xi dxi with a sum over I. And this is exactly what has been written over here. So if I have a function which is like this, if I draw the analogy with this, then it immediately follows that del f del x is a of xy and del f del y is b of xy. But since it's an analytic function, it follows that the mixed derivatives must be the same. Del 2f, del y, del x. So therefore it follows del a del y, which is essentially del l. If you look at this, this is equivalent to del y of del f del x. And if you look at this, this is equivalent to del f del y del x of this. If I now put it over here and put this one over here, then it follows that del f del y, del a del y must be del b del x. If this is the condition that is satisfied, then the function f of, or rather d of fxy is an exact differential. If it is not, then the function is an inexact differential. And if it's an inexact differential, then the value of the integral d of fxy over a contour c will depend on the contour that you have chosen. If it's an exact differential, then this value is only dependent on the initial point and the final point. Right. So therefore, the first law essentially tells you d cut q is du minus d cut w. Now remember, in the last class we have seen that of all these generalized macroscopic variables, the thermodynamic variables that describes the system, some of them are extensive and some of them are intensive. And the intensive ones are what we call them as generalized forces. And we will change their notations from x to fi. On the other hand, the extensive variables are generalized coordinates, and they depend on the system size, and we will keep them as fi. So that the work done, and here also again I am drawing the analogy from mechanics, is sum over I fi dxi. So the whole game in thermodynamics is to identify this macroscopic variables and then find out from which of these are your generalized forces and which of these are your generalized coordinates. Once you have identified them, then you can write down the work done like this way, and it follows therefore that your first law takes the form sum over I fi dxi. First law of thermodynamics. Right? Interestingly, you cannot design a machine which violates the conservation of energy. So machines which violate the first law are not allowed. So these are machines which are called perpetual machines of the first kind. You cannot have perpetuous machines of the first kind because you are violating the conservation of energy.